Hello, dear friends. After completing unit number 6, let us move towards unit number 5, flow through pipes. Let us divide this unit in three sections. First, major and minor losses and the terms involved under it and the numericals based on them. Second, siphon, pipes in series and pipes in parallel and the numericals based on it. And the third part, dimensional analysis or dimensionless numbers, model analysis and numericals based on it. So let us come to the first part of this unit. I have divided this complete unit into three sections. So out of that, first section, that is losses in pipes, that we'll see now. Generally, we know whenever the flow takes place in the pipe, the fluid experiences some resistance due to friction, that is because of shear stress, due to which the energy of the fluid is lost in overcoming that friction or the shear stress. And this loss of energy is nothing but it is also called as a loss of head. So there are two types of loss. One is called as a major loss and other one is called as a minor loss. What do you mean by major loss and what do you mean by minor loss? That we will see in this lecture, in this video in detail. Major energy loss, it is because of mainly friction. The friction is the major cause of the major energy loss. So the loss which is because of friction between the fluid layers as well as fluid and solid, that is called as a major energy loss. And second, the minor energy loss. The minor energy loss, this is nothing but because of the area change of the pipe. If there is sudden change in the cross section area of the pipe during the flow, then the fluid experiences some loss. That is called as a minor energy loss. But compared to major energy loss, these minor energy losses are very small. That's why in many cases these minor energy losses are neglected. But they cannot be neglected always. For that, we have to consider the minor energy losses also in some cases. So let us first see what do you mean by major energy loss in detail. If you see the major energy loss which is because of friction, that is given by the famous scientists Darcy and Wisbach, who has given an equation that is given by Hf is equal to 4FL V square upon 2GD. This is a very famous equation and it is used worldwide today. For calculating Hf, given by the formula 4FL V square by 2GD, in this formula the term f, small f, is called as a coefficient of friction. Remember, the term small f is called as a coefficient of friction, and small l, capital L is called as the length of the pipe, capital V is the mean velocity of the fluid through the pipe, small d is the diameter of the pipe. So in this formula, only the important term is the small f, which is called as the coefficient of friction. And how to calculate this small f, that is very important for solving the numericals based on the major loss. So we have already seen in unit number 4 what do you mean by laminar flow and turbulent flow. If Reynolds number is less than 2000, then the flow will be laminar, and if it is greater than 4000, then the flow will be turbulent. Depending upon the flow, whether it is laminar or turbulent, this coefficient of friction varies. If the flow is laminar, that is Reynolds number is less than 2000, then the coefficient of friction small f is called as a 16 upon Re, Reynolds number. And if the flow is turbulent, then the coefficient of friction is given by 0.079 upon Re raised to 1 by 4. Remember, the Reynolds number should come greater than 4000 for turbulent flow. So it is very simple to calculate F based on the Reynolds number. So for that, first you have to calculate the Reynolds number. We have already seen the Reynolds number is calculated as rho Vd by mu for a pipe. So you have to use the formula rho Vd by mu to calculate Reynolds number. Put the value of Reynolds number, whether it is laminar or turbulent, in the given formula. You will get the value of f, small f. Okay. Now, one more thing I want to tell you here, that the term small f is called as the coefficient of friction, while in some books you will find there is a term which is given as a combined term replacing 4 into f, that is 4f. If there is a term which is generally given as f dash, then that f dash is nothing but the replacement for 4f. So in many books you will find the formula hf is equal to f dash lv square upon 2gd, where f dash is nothing but 4f, and that is called as a friction factor. So remember the difference between the friction factor and coefficient of friction. Friction factor is 4 times the coefficient of friction. So you have to carefully find the value of f. By using the formula 16 upon Re, you are finding the coefficient of friction. So you have to use the appropriate formula to calculate the coefficient of friction. For friction factor, you have to multiply the coefficient of friction by 4. Okay. So this is very important. Now let us see some numericals for major loss. The numericals are very simple. Let us see first numerical. Calculate the discharge through a pipe of diameter 200 mm when the difference of pressure head between the two ends of the pipe 500 meter apart is 4 meter of water. Take the value of small f is equal to 0.009 in the formula hf is equal to 4flv square upon 2gd. Now it is very simple problem. In this problem, if you see, first write down the given data. Small d is equal to 200 millimeter, 0.2 meter. Capital L, it is length of pipe is 500 meter. Difference of pressure head, that is loss of head is given. Pressure head is given. HF is equal to 4 meter of water. And small f is equal to 0.009. So we have the formula HF is equal to 4FL square upon 2GD. Now in this formula we have been given the value of coefficient of friction as a ready-made value. In most of the cases it is not given. You have to calculate the value of F by using the formula either for laminar flow or turbulent flow. For that first you have to calculate the Reynolds number. But in this you have been given the value of small f as a ready-made value. Put that value of small f in the given formula. Here you have to calculate the velocity V, because the aim of the numerical is to calculate the discharge through the pipe, and discharge is given by area into velocity. So first you have to find velocity. So you will get the value of velocity by putting the other values in the formula hf is equal to 4flv square upon 2gd. So if you put 4 is equal to 4 into 0.009 into 500 into v square upon 0.2 into 2 into 9.81, you will get the value of v, that is the velocity through pipe, as 0.934 meter per second. And it is very simple to calculate discharge from the velocity, as it is given by velocity into area. So area is pi by 4 d square. So you will get the discharge as pi by 4 into 0.2 square multiplied by the velocity 0.934, that is coming as 0.0293 meter cube per second or 29.3 liters per second. So it was very straightforward problem. Now let us see one more numerical where you have to calculate the coefficient of friction based on the Reynolds number. So for that you have to first calculate Reynolds number, and then you have to put the value of Reynolds number in the formula to calculate small f, depending upon whether the flow is laminar or turbulent. So let us see second numerical. A crude oil of kinematic viscosity 0.4 Stokes is flowing through a pipe of diameter 300 mm at the rate of 300 liters per second. Find the head loss due to friction for a length of 50 meter of the pipe. Now here the kinematic viscosity is given 0.4 Stokes, which is calculated as 0.4 centimeter square per second or 0.4 into 10 raised to minus 4 meter square per second. Diameter is given as 300 millimeter or 0.3 meter. Discharge is 300 liter per second. Converting, you will get 0.3 meter cube per second. Length of the pipe is 50 meter. Everything is given. The velocity you have to calculate from the discharge, because we will require the velocity in the formula hf is equal to 4flv square upon 2gd. So first you have to calculate the velocity, and velocity is also required to calculate the Reynolds number. So velocity, it is discharge upon area it is coming as 0.3 upon pi by 4 into 0.3 square. It is 4.24 meter per second. Reynolds number, you know, it is rho Vd by mu. But here mu by rho, we know it is nu. So you can also write the formula as Vd by nu. And it is coming as 4.24 into 0.3 upon 0.4 into 10 raised to minus 4, which is 3.18 into 10 raised to 4. That is coming as a greater than 4000. So the Reynolds number is greater than 4000, hence the flow is turbulent. And we know the formula for finding the coefficient of friction for a turbulent flow as F is equal to 0.079 upon Re raised to 1 by 4. Putting the value of Reynolds number in that formula, you will get the value of coefficient of friction as 0.00591. Putting this value of coefficient of friction in the formula HF is equal to 4FLV square upon 2GD, you will simply get the value of HF, loss of head due to friction. So there is a loss of head as a 3.61 meters. So this is the answer for the second numerical. I hope the numericals on major loss are clear now. Let us see the second more important loss, that is called as a minor loss. Now minor loss, it is also an important type of loss. Already I have told you the reason behind the minor loss. Minor loss is happening because of the area change of the pipe. So if there is sudden change in the area of or the shape of the pipe, then there will be loss, that is called as a minor energy loss. So now major loss was due to friction, minor loss is due to change in area. There are certain types of minor losses because the area changing may may it be increasing area, it may be decreasing area. So depending upon that, the minor energy losses are having certain types. So let us see one by one. There are total 6 or 5 types of losses which are coming in minor losses. So first, loss of head due to sudden enlargement, loss of head due to sudden contraction, loss of head at the entrance of the pipe, loss of head at the exit of pipe, and loss of head in various pipe fittings such as elbow, bend or coupling. So all these are nothing but the shape or area change types. That's why there are many types coming under minor losses. Now the name is minor loss. That means the value of minor loss by the calculation is going to come less than major loss. That's why its name is given as minor energy loss. So many times the minor losses are very less compared to the major loss, and hence they are neglected. They are neglected in many numericals. But as far as the short pipes are concerned, the minor energy losses are considered for the calculation. So it depends. Now you remember, the in case of the long pipes, the loss of head due to friction or the major loss is more, because major loss formula, you know, HF is equal to 4FLV square upon 2GD. So higher the value of L, higher will be the value of HF. While in case of longer pipes, or you can say in case of the pipes having more lengths, major loss is more, but the minor losses are many times neglected because their values are coming very less for long pipes, and that's why they are neglected. But the minor loss values have to be considered in case of the smaller pipes because they are comparable with the major losses. So for the short pipes, you have to consider the minor losses. Now how to calculate these minor losses? So here we will see only the formula for the different types of minor losses. So first one, let us see loss of head due to sudden enlargement. If you see the figure there, the pipe area is increasing, suddenly increasing. That's why the velocity is reducing, because area is increasing, velocity is reducing. So there is a kinetic energy loss across this, and that is given by He is equal to V1 minus V2 bracket square upon 2G. So you remember the formula for loss of head due to sudden enlargement or expansion as HE is equal to V1 minus V2 bracket square upon 2G, where V1 is the velocity in the smaller pipe and V2 is the velocity in the larger pipe. Second type, it is loss of head due to sudden contraction. Here the area is decreasing. Now it is a reverse case than that of the first case. So here the velocity is increasing because area is decreasing, but the pressure is decreasing. So velocity is increasing but the pressure is decreasing, so there is a loss. So loss does not mean that there is only pressure loss or velocity loss or datum loss. Loss means overall loss. It may be pressure loss or velocity loss or kinetic energy loss or datum loss. So here in this case the loss of head is given by a formula. Okay. There is a derivation for it, but let us see only the formula, which is given as HC for head loss due to contraction as 0.5 times V2 square by 2G. Remember this formula. In most of the cases the value of K, which is constant, is taken as 0.5. So hence it is the loss of head due to sudden contraction, that is HC is equal to 0.5 V2 square by 2G, where V2 is the velocity in the smaller pipe. Velocity in the smaller pipe. Okay, that you have to remember. Third, loss of head at the entrance of the pipe. At the entrance of the pipe means when there is a pipe connected to a tank, then there is a entrance to the pipe. From the tank the flow is entering into the pipe, so there is also sudden contraction of the area. So at that case you have to consider the entrance loss. That is called as the entrance loss because it is contraction in the from the tank to the pipe, not from the pipe to the pipe. That's why it is called as the entrance of the pipe loss, but it is calculated by the same formula which we are calculating for sudden contraction. It is given by HI is equal to 0.5 V square by 2G, because in the tank there is no velocity to the fluid, only the velocity is in the pipe. So you have to consider the velocity in the pipe, velocity of fluid in the pipe, which is given by HI is equal to 0.5 into V square by 2G. Then there is a loss of head at the exit of the pipe, which is HO. Okay, at the exit the energy is lost in the form of kinetic energy, so it is given by V square by 2G. And last is a loss of head in various pipe fittings, now such as elbow shown in the figure. If you see, then it is given by KV square by 2G again. So that loss which is due to pipe fitting like elbow, bend or coupling, it is generally given by KV square by 2G, and the value of K is ranging from 0.25 to 0.3. So many cases it is taken as 0.25 to 0.3 depending upon the angle of the elbow or depending upon the type of the pipe fitting. Okay, generally in case of bend it is taken as 0.25 V square upon 2G. So the value of K is also given for this. Now let us see some numerical based on the minor loss. Determine the rate of flow of water through a pipe of diameter 20 cm and length 50 meter when one end of the pipe is connected to the tank and other end is open to the atmosphere. The pipe is horizontal, height of water in the tank is 4 meter above the center of pipe. Consider all minor losses and take coefficient of friction as 0.009 in the formula HF is equal to 4 FLV square by 2GD. In this numerical, you have to consider both the losses, major loss as well as minor losses, because it is given the formula for HF also. So just you have to use the Bernoulli's equation which we have seen in unit number 3. If you remember the Bernoulli's equation, it is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. HL is nothing but the loss of head. Okay, whether it is major loss or minor loss. So all we are going to consider here. Now if you see in the numerical, just write down the given data: diameter of the pipe, length of the pipe, height of water tank or water inside the tank, and coefficient of friction small f, and the velocity of the pipe, it is V. Velocity of flow in the pipe, it is V. That you have to calculate first, and then you have to solve for the major and minor losses. Now using the Bernoulli's equation, we have already seen it is P1 by rho g plus V2 V1 square by 2g plus Z1. Now Z1 is equal to 4 in this case. In the numerical, if you see, Z1 is nothing but the height, that is 4 meter. What about P1 and V1? It is inside the tank. P1 is 0, V1 is 0. Okay, no velocity, stationary fluid, is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL, or all the losses. P2 by rho g, again it is in the atmosphere at the end of the pipe, so it is again 0, atmospheric pressure. V2 is the velocity inside the pipe, velocity V. Z2, it is the datum, is the center line of the pipe, so it is 0. And the losses will be, one will be the major loss HF, and other one will be the entrance loss. At the pipe entrance, there will be loss of head due to entrance, and that is given by 0.5 V square by 2g. So that entrance loss you have to consider. Don't consider exit loss here, because in the Bernoulli's equation already we have considered V2 square by 2g. So that is all again, it will be the repetition. Already we are considering V square by 2g. Exit loss is also given by V square by 2g. So no need to take again. Already we have taken into consideration that loss inside the Bernoulli's equation. So don't write the exit loss. Only entrance loss and the loss of head due to friction, or the major loss. So now let us see, 0 plus 0 plus 4 is equal to 0 plus V square or V2 square by 2g plus 0 plus HI, it is entrance loss, plus HF, it is friction loss. So 4 is equal to V2 square by 2g plus entrance loss plus friction loss. Velocity V is taken instead of V2. So 4 is equal to V square by 2g plus HI plus HF. HI is entrance loss 0.5 V square by 2g. HF is friction, loss of head due to friction, which is given by Darcy-Weisbach equation, 4FL V square by 2GD. So 4 is equal to, again coming as V square by 2g inside the bracket 1 plus 0.5 plus 4 into 0.009 into 50 upon 0.2. And if you do the calculations, you will get the velocity as 2.734 meter per second. Putting the velocity in the equation of discharge, discharge is equal to area into velocity, you will get the discharge. It is coming as 0.08589 meter cube per second, which is 85.89 liter per second. So this is about the numerical of the minor loss. Now let us see the last portion of this section, that is the hydraulic gradient line and total energy line. So already we have seen that there are losses happening in the form of pressure loss, velocity loss or kinetic energy loss, and datum loss or potential energy loss. So these three loss, that is pressure energy loss, kinetic energy loss, and the potential energy loss or datum energy loss, these three losses are considered while defining the term total energy line as well as the hydraulic gradient line. Now you will see what is the difference between these two, the total energy line and hydraulic gradient line. Remember, in total energy line we have considered all these three energies: pressure energy, kinetic energy, and datum energy or potential energy. While in hydraulic gradient line we are neglecting the kinetic energy losses and or the kinetic energy term while considering the energy. So if you neglect the kinetic energy term, then the remaining two terms are pressure energy and datum energy or potential energy. So that line which will be joining the points of pressure energy plus datum energy or potential energy, that is called as a hydraulic gradient line. And the line joining the pressure energy plus kinetic energy plus datum energy, that is called as a total energy. The things will be very clear from this figure. If you see the figure, there are the three terms shown above the datum line. If you see datum plane, above the datum plane there is Z1, P1 by rho g, and V1 square by 2g. Okay, for section 1. So Z1 is datum energy, P1 by rho g is the pressure energy, V1 square by 2g is the kinetic energy for section 1. For section 2, for the second pipe, you will see that it is Z2 P2 by rho g and V2 square by 2g. For section 3, Z3 P3 by rho g and V3 square by 2g. Now if you see at the top of the figure, there is one line which is called as the energy line, and that energy line is nothing but that line is considering the total all the three types of losses, all the three types of energies. One is datum energy, pressure energy, and kinetic energy. So the line representing all these three energies joining across the all the pipes, that is called as the energy line, total energy line or energy line. Why it is decreasing? The line is decreasing because of the losses H2 and H3. H2 are the losses which are sudden expansion as well as friction across the pipe 2, and then H3, it will include the loss due to sudden contraction and friction across the pipe 3. So if you subtract the loss of head due to these major as well as minor losses, then you will see that the energy goes on decreasing from right from tank 1 to tank 2. Okay, that is called as a loss of head. So the total energy line and the hydraulic gradient line are nothing but the lines showing the energy transfer phenomenon or the losses of head or loss of energy happening across the flow of the pipe. So I think the first section, that is the losses is in pipe, and the terms involved under that we have covered in this lecture. I hope you have understood it. Just make practice, some more practice on the numericals based on the major loss and minor loss. They are very simple. Best of luck. Thank you.